First, thank you for the invitation, and also since I am the last speaker of this workshop, maybe let's first all thank the organizers for this very nice workshop. Okay, and so now let's turn to the math. So today I'm going to present some recent work on the construction of a so-called level line for the massive GFF. So the goal is to define a random curve that can be seen as the level line of a random field called the massive GFF, which is a field defined on a subset of the complex plane. But okay, before entering into the problems per se, let me give some motivation. So this question comes from the question of, okay, what is the scaling limit of interfaces in planar statistical mechanics models. So, okay, what does this mean? Well, let me give you some example to motivate the question. So, okay, so let's say you have some domain D, which is a bounded subset of the complex plane, and also simply connected. Okay. And let's say that you have a lattice approximation of D that I'm going to denote by d delta, where delta is the mesh size of the lattice. And okay, typically you should think of the square lattice or the triangular lattice. Okay? And then, okay, so examples of this object, so of interfaces in planar statistical mechanics models are, okay, for example, the following, so-called loop-arrays random walk. So in that context, okay, you approximate the domain D with the square lattice of mesh size delta, and on this lattice you have two marked boundary points, say A and B, and you sample a random walk from A to B, and then you erase the loop. So you're going to obtain a path that does something like this, say. Okay. And then the question is, okay, you let delta goes to 0, where, once again, delta is the mesh size, and you ask yourself, okay, what is the scaling limit of this random curve, if any? And it turned out that it has been shown to be described by a random curve that is called SLE2. So we've already encountered this object in Antoine's talk. So SLE stands for Schramm-Lerner evolution, and 2 is a parameter. And one very important property of this object is the fact that the law of SLE2 is conformally invariant. So if I take a conformal map from D to another domain, then the image of the curve will again be an SLE2 in this new domain. But okay, the position of the mark point will have changed. So another example is the Ising model. So in that case, you have a collection of spins on the vertices of d delta. So these spins, they take value plus or minus 1, and they are distributed according to the following probability measure. So you have exponential time beta, which is called the inverse temperature, and then you have a nearest neighbor interaction between spins. And okay, you can get an interface on your lattice if you impose appropriate boundary condition to your model. So let's say you take the square grid, and then you decide that all your spins are minus on one part of the boundary and plus on the other. And if you do this deterministically, you will have an interface on this lattice so that on the left you will have minus spins, and on the right you will have plus spins. And then you can ask the same question, namely, okay, what happens when I let delta goes to 0 in this picture? And it turned out that if you choose your inverse temperature beta here appropriately, so it has what's called a critical value. So if you take beta to be the critical parameter, then in the scaling limit, you will get another Schreiber evolution, but no with parameter 3. Okay? And once again, this SLE3 curve is conformally invariant, just as in the same sense as SLE2 was. Okay. And then let me mention a last example, which is that of the discrete GFF, and this will become important later. So the discrete GFF, so here for this example you should think of the delta as being the triangular lattice. So the discrete GFF is just a random height function so that you have a multivariate Gaussian random variable on the vertex of your graph. So it is like in Alexei talk yesterday. This. Okay. And then if you impose appropriate boundary condition to this object on your lattice, and you say, okay, a vertex has sign minus if, so you take your triangular lattice, and each point on your triangular lattice can be surrounded by an hexagon. And if you assign a sign to each hexagon according to the sign of the vertex that is surrounded by the hexagon, then you will get an interface separating plus and minus hexagon. And this interface, you can ask exactly the same question. What happens to it when I let delta goes to 0? And it turned out that you get another SLE curve, but no with parameter 4.
I'm sorry, I didn't understand how you assigned the plus minus.
So if you have your triangular lattice, you can draw hexagons around each.
Yes.
Okay, and then this vertex, it is say h of x, and h of x is
the sign.
Yeah, the sign.
Okay.
So either less than 0 or okay. Okay. So now this is enough for the example, and now let's go to the problem.
So that will be the interface between positive and negative h.
Yeah, exactly. And so now okay, so we have this picture that somehow when you are at criticality, so when you take beta critical here, when here somehow it's like critical in the sense that random walk converge to Brownian motion, here you get the GFF in the scale limit. Okay, we understand that at the level of the interface, we get some kind of SLE curve. And then, okay, a few years ago, Markov and Smirnov raised the following question. So what happens? So what happens to this interface when we perturb the models in a near critical way? So I'm not going to explain exactly, like to give a general definition of what it means to perturb the model in a near critical way, but I'm just going to explain what would happen in those previous examples, and we'll see a little bit what changes. So in the case of loop array van der Moog, what you could imagine is instead of having a random walk as your basic object, you will consider a killed random walk. So you will kill it at some rate, and if you want to be in the near critical regime, you have to tune the mass, so the rate at which you kill the random walk, appropriately with delta, and the scaling is given by m squared delta square, just because then the massive random walk converges to ball and motion killed exponential rate. So in the case of the Ising model, one thing you could imagine doing is, okay, I told you have this critical temperature, so you could imagine perturbing the temperature, and in that case, the scaling in delta is actually proportional to delta, so you can have this kind of perturbation. But in the case of Ising, you could also perturb it another way by adding an external magnetic field to your model. So you would instead consider the model with, so you will still be at critical temperature with the same interaction between spin. But then you would add on a magnetic field, and in that case you have to tune it as delta 15/8 and then spin. And then for the discrete GFF, well, basically you could do exactly the same as in the case of the loop array van der Moog, namely you consider the massive discrete GFF. And this is just given by perturbing the field by a mass. So you will still have 1/8, and then this Dirichlet energy, but then minus m squared delta square, and then in that case it's the total mass of the square of the field. Okay, and in all those models you still have this those interfaces on your lattice, and then the question is, okay, can I do exactly the same thing? Namely, can I take the limit as delta goes to 0 to in these models? And here, if you know a little bit about SLE, there is something that changes. That because you are in the near critical regime, in the scaling limit, you don't expect conformal invariance. Like the mass introduces a finite correlation length. And as a result, you lose all the nice characterization tools that we have for SLE curves. Okay, but now what we are going to do is to focus on this object, and we are going to try and answer the question of Markov and Smirnov in the case of the massive discrete GFF. Okay, so let's say if I write here, can everyone see or? So let's say you want to answer the question in that case. Well, what can you say? So maybe, okay, the first remark that is in the discrete a bit trivial, but that will become important, is that the interface, so the interface, so whether you are in the massive case or in the non-massive case here, the interface, so if you denote it gamma, so this interface is measurable with respect to so to your field, so to h of x. And then the other important thing you can notice is that okay, the massive discrete GFF and the discrete GFF are absolutely continuous with respect to each other. And you can actually compute the Radon-Nikodym derivative. So and this is given, okay, this is proportional to exponential minus m squared delta square over 2, and then the total mass of the square of the field. So then, somehow, thanks to this, you directly have a change of measure that gives you the law of the pair field interface in the massive setting. So it gives you the change of measure with respect to the pair interface field in the non-massive setting. So namely, you can write, so what you get is that you can actually have a change of measure on the coupling, if you prefer, between your interface and your field. And okay, this is given by exactly the same thing. So now, basically, if you want to answer this question, so the question of what happens to the scaling limit of the interface, one way is to understand what happens to this coupling and the scaling limit as delta goes to 0. So it's not exactly how I'm going to do to construct the limiting object in what follows, but basically the strategy will be exactly the same as the one that I've just outlined. And so now what I'm going to do is that, okay.
There's a special thing.
Okay. Well, I can just erase. Okay. So the
The others are okay, I think.
Okay. Okay. So what I'm going to do is instead to work directly in the continuum. So I'm going to work with the Continuum GFF, the Continuum Massive GFF, and then SLE4 directly, and then I'll construct everything in the continuum. But okay, so for this, I need to give you somehow all the definition that we need to go on. So let's start with the Continuum Massive GFF. So I think we've already more or less encountered this object in Titus and Nathaniel's talk, but just let's be clear on it. So here, and for the rest of the talk, I will have a bounded domain D, which is a subset of the complex plane, and okay, I'm also taking it simply connected. And then on D, I have a mass. so a mass function that goes from D to R plus, and I'm assuming this mass to be bounded. Okay. And in this setting, the massive GFF, so the massive GFF in D is the Gaussian process H index, so it's indexed by functions that are smooth and compactly supported in my domain. And it has mean 0 and covariance given by, so if I take two functions, f and g, that are smooth and compactly supported in D, then the covariance is given by the following. So I test f and g against the kernel GMDZW, where this GMDZW is the massive green function. So this is, if you prefer, this is just the inverse of minus the Laplacian plus m squared in the sense of distribution. And really, this object is nothing else than the scaling limit of the massive GFF. And when you take m equal to 0, you recover the usual GFF. And okay, I think it has already been said this week, but this object is not defined pointwise. It's a random distribution. And okay, nevertheless, you should view it as being somehow 0 on the boundary of my domain D, because if I take a point Z in my domain D and a point W on the boundary of D or outside D, then this massive green function is equal to 0. Okay. So, and maybe also let me stress one property of this massive GFF. It's that, okay, we've said that in the critical setting, all those SLE curves, they are conformally invariant, and that a priori, when we put on a mass, we lose this conformal covariance. So you can already see it at the level of the field, in the sense that this object, so the massive GFF, is conformally covariant. So if I have my domain D, okay, and then I take conformal map psi to another domain D prime, and here I have my mass M, and then I have a new mass here, and this new mass, so actually it's square, it's given by, you have a factor coming from the modulus of the conformal map, and then the original mass. This is the way you have to change the mass when you go from one domain to another, and in particular, okay, if you take m equal to 0, you recover the fact that the GFF is conformally invariant. So this is for the definition of the field. And now, if you remember, I say, okay, in the discrete, I have this coupling between my GFF, my discrete GFF, and my interface. And this coupling also exists in the continuum, and it's called the GFF, it's a full coupling. So, but before kind of introducing this object, I just need to tell you a little bit about what it means for the GFF to have non-zero boundary condition, because it's something I've hidden a little bit in the background in the discrete, but those boundary conditions that plays an important role. So I will just give a quick definition. So let's say I have a function f defined on the boundary of my domain, which is bounded. Then the massive GFF with boundary condition f has the same law as h plus something that I'm going to call phi mf. So this h is just a massive GFF in the sense of this definition, and this phi mf is the massive extension of f. So it solves the following problem. So its massive Laplacian is equal to 0 in D. And then, okay, it's equal to f on the boundary of okay. And so then, now that I have this, I can state this GFF SLE4 coupling. So this is a result due to from Sheffield. And okay, what does it say? So I need to introduce some more data in some sense. So I will still have my domain D, but now on the boundary of D I have two mark points, A and B. And I'm going to define this constant lambda, which is going to be fixed for the rest of the talk, and it's going to be equal to square root pi over 8. Doesn't matter what it has to be this value, but it has to be this value. Then phi this will be the harmonic function with boundary condition plus minus lambda. So you will have minus lambda here and lambda here. Okay? And you just take the harmonic extension for this. And so in this setting, you have the following results. So there exists a coupling so between the GFF with boundary condition plus minus lambda and a curve, so an SLE4 curve in D from A to B, where you remember SLE4 was the scaling limit of the interface in the discrete GFF. And in this coupling, so if I condition my field on gamma on my curve going up to some time t, then I get the following. I get that h plus phi is equal to ht plus phi t, where you should just think of this picture. So you have your domain D, your 2 mark point, and then you grow gamma for some time. And what you have in the slit domain, so in the domain minus the curve, is ht. So this is just a GFF in the slit domain. And then this phi t is just the harmonic function with boundary value minus lambda lambda, and then lambda on the left of the curve and minus lambda on the right of the curve. So you get this kind of dynamic picture. And importantly, gamma is measurable with respect to h. And in that sense, you can really view gamma as an interface of your continuum GFF. Okay? But yeah, so this result is really when you have mass 0, and then the question is, okay, what happens when you have non-zero mass? So when you introduce the mass. And so it's what I'm going to explain just now. And for that, we are just going to carry out the program that I outlined in the discrete, but in the continuum. Know that we have all the tools. So, okay. So the only thing that I didn't say in the continuum is this question of absolute continuity and of the Radon-Nikodym derivative between the massive GFF, so with a mass, and the GFF. So let me just take this as a lemma, maybe. So this PM will be the law of the massive GFF, and then I have the GFF. And I'm going to state the result for when the fields have non-zero boundary condition, because it's what will be needed. And then, okay, this is proportional to exponential minus 1/2 time an object that I'm going to explain in a minute. So So what is this? So if you remember, in the discrete, the Radon-Nikodym derivative was given by exponential minus m squared delta squared over 2, and then the total mass of the square. But I've told you that in the continuum, the GFF is not defined pointwise. So apparently it's not clear in the continuum how to make sense of this object. And so this random variable here, which is called the weak square of the field, and that Titus mentioned the other day, is a renormalized version of the square of the GFF, and is just defined as follows. So if I call this W2 of h plus phi, the way you can define it is, so what you do is you regularize your field, let's say by modifying against a smooth function, so that it makes sense pointwise, and you can take the square as you would do. But then you know that the variance of this object is going to blow up, so you subtract this, And it turned out that the only thing you need to remove, and then you take the limit as epsilon goes to 0, and you get a random variable that is well defined in L2. Okay, so this is in particular, this is not an integral. This is just some notation, and this is something obtained as a limit. Okay, so now let's see what we get if we use all the object I've introduced. So you remember we want to construct this coupling for the massive GFF. So then we can do just as in the discrete. So I'm going to call I'm going to call P the law of the Sheffield coupling over there. And then I'm going to define a new measure. Yeah, it's Radon-Nikodym derivative with respect to P. So P tilde will be a measure on pair field interface. And the Radon-Nikodym derivative will be given exactly as somehow in the discrete. So minus 1/2 times the weak square of the GFF. Okay, and then let's see. So this is a change of measure on the pair H plus phi gamma field interface. And in that case, if you do this, what you get, it's a bit obvious, but H plus phi, let's just write it, is a massive GFF with boundary condition plus minus lambda. But here, remember that in the massive case, we are taking the massive harmonic extension of the boundary condition. And then, so I can ask the same question as in the Sheffield coupling, namely, what happens if I condition on the interface? But under P tilde, so under P tilde, conditionally on gamma, going up to some time t, I can decompose H plus phi as ht plus phi t, where the picture is exactly the same as in the massless setting, in the sense that if you have your domain D, and then your interface, this phi t will be the massive harmonic extension of the function with boundary condition lambda minus lambda, and this ht is a massive GFF in your slit domain. Okay, so somehow we got exactly the same result as here, but when the mass is present.
What is the law of gamma here now?
I will come to it in a minute. Don't worry. Okay, I can erase this. So before telling you a bit more about the law of gamma, just maybe let me explain why you get this decomposition when you do this change of measure, and then I will say what is the law of gamma. So, okay. So, so if you want to prove such a conditional decomposition, one thing you can look at is the characteristic function of your field given gamma got m2 time t. So this is exactly what we are going to do. But no, okay, of course we are under p tilde. And okay, for the sake of the argument, I'm just going to pretend that h is defined pointwise so that I can take the square as if it was a normal function. So I can just apply the definition of p tilde. So I get h plus phi f, and then I have this exponential minus, and then m square h z plus phi z square dz. Then, sorry, condition on gamma. And then I have 1 over zt, that's somehow a random normalization constant. I'll come back to it in a minute. But okay, it's very nice because we're under P. So we know exactly the conditional law of h plus phi given gamma. So this is h plus phi t, okay, as in the Schramm-Sheffield coupling. And moreover, I also know that SLE4 almost surely has Lebesgue measure 0. So this integral, instead of doing on the wall of D, can just be on the slit domain D minus the interface. And then VZT, so VZT is just what makes everything a random probability law. So this is the total mass of the square, well, exponential of the square. And then conditionally on gamma. But then I can play the same game, right? I'm on the P, so this is ht plus phi t, and then, okay, SLE4 almost surely has Lebesgue measure 0. But now, if you look at this lemma that gives you the Radon-Nikodym derivative between the massive GFF and the GFF, well, this is exactly what you have here, conditionally on gamma. So this is why you have the result over there. So of course, it's a formal proof because the GFF is not defined pointwise, but it turned out that if you take the exponential minus of the epsilon regularization of your weak square, you have convergence in LP of this object to exponential minus this weak square, and so you can just somehow do an exchange of limit, work at scale epsilon so that everything is defined pointwise and you can apply Schramm and Sheffield result, and then you just have to make sure that when you take epsilon to 0, everything behaves well. Okay, but so as you've just asked, this result is a bit incomplete because I haven't said anything about the marginal law of gamma. So this is the next question. Okay, but for this you can make an observation. So let's say you pick a point D in your domain D, and then I'm going to call it doesn't matter how it's called. This is the massive harmonic measure So this is a massive harmonic measure of the cycle of radius epsilon around z seen from. So this is exactly the same thing as the usual harmonic measure, but now you're considering Kiel-Brunner motion, if you prefer. And then, okay, what can you say? If you look at the conditional expectation of h plus phi tested against this massive harmonic measure, conditionally on gamma going up to some time t under p tilde. So if you look at this conditional expectation, you know what is the conditional law of the field, thanks to this. So you will have a massive GFF in the slit domain, so this just has a mean 0, plus a massive harmonic function. So when you test it against massive harmonic measure, you just get the function itself. If z is if epsilon is smaller than the distance between z and the curve. But okay, what does this tell you? Like this very short calculation. Well, this tells you that phi mt z as a process indexed by t is a martingale. For the filtration, well, let's say the natural filtration of gamma, just because this left-hand side is a martingale by definition. Okay? And it turned out that it's also true for all points. So if you know a little bit about SLE4, this should remind you of the Martingale characterization of SLE4. And it turned out that you can extend this result to the massive setting. So namely, you have the following proposition. There exists a unique law on a non-self-intersecting curve from A to B in D such that for any z in the domain D, phi mtz is a martingale. Okay, we are going to call this law massive SLE4. From A to B. So a few comments about this. So massive SLE4 was originally introduced by Markov and Smirnov to describe the scaling limit of a massive version of the harmonic explorer. And also, for those who know a little bit about Schramm-Lerner evolution, the way you prove this proposition is by computing the driving function of your curve. So I could also give you the driving function, but the expression is a bit complicated. So if you're really interested, you can ask me at the end. Otherwise, I will just skip this. Okay, and maybe so as a corollary. Well, the marginal law of gamma and the tilde is massive SL4. In particular, it tells you that the law of massive SL4 is conformally covariant because somehow you inherit this property from that of the massive GFF, and that the way the mass changes from one domain to another changes exactly as for the massive GFF. So I think it's everything I wanted to say about massive SL4 and the massive GFF. I will just mention one thing. So for those who know a little bit about CLE, kappa, SLE, kappa, and so on, you can also apply the same kind of ideas when your massive GFF has zero boundary condition to construct a massive version of CLE4. And in that case, what you get is, okay, a collection of simple loops that almost surely do not intersect the boundary of the domain and do not intersect each other, and that are the level lines of your massive GFF with zero boundary condition. And you can also show that this massive CLE4 can be constructed by first sampling a Brown loop soup, then with some appropriately chosen intensity, then killing the loops independently according to the mass, and then taking the outer boundaries of the outermost clusters, and then what you get is a massive CLE4. So this is the analog procedure as in the massless setting. Okay, and then yeah, then I think it's everything I wanted to say. So thank you for your attention. And
Editors?
Could you please give the expression for driving function?
you want the driving function? So this is, so you have 2 times the Brownian motion, so just as in the massless setting, plus, actually minus the drift. So you have some constant, and then this is the integral over the slit domain, then m square, okay, then hm, so actually I've called it Im tz. So this is a massive harmonic function with boundary value lambda minus lambda. And then you have ptz, dz. So ptz is the, if you prefer, is the Poisson kernel, well, the boundary Poisson kernel evaluated at z and the tip of the curve. So, and yeah, this is the drift.
Any other questions?
That's a bit related, but you get nice things for specific traces of M.
Do I get specific things? I don't know. I'm not sure.
maybe it's a particular case of what you've said, but if you wanted to look at the, say, you start with this discrete field, but with a mesh delta, and instead of looking at the level line of 0, right, you look at the level line of delta or square root of delta or whatever the right scaling is. Or I mean, if you want to perturb, if you want to look at level lines at a different height than 0, and possibly this height would go, if you are in this discrete case, possibly this height would go to 0 when delta goes to 0. Is it included in what you do?
I don't think I understand the question. So
instead of looking at the level line of the free field at 0,
okay.
you look at the boundary of the level set of h, different value.
Okay, some value of h.
Yes. Is it included in your case?
Is it included in my case? Maybe not directly, but I think you could use the same kind of techniques. Yeah, because you would have the same kind of Radon-Nikodym derivative. I think yeah, I guess. But yeah, what is not included in my case is if you wanted to get the coupling from the discrete, you would have a little bit of work to do because, okay, it's hidden in the background, but an important things to make the proof works is that the square of the field does not give any mass to your curve, and this is because somehow the way you renormalize the field doesn't see the curve in some sense. And the discrete, to have this kind of analogous things, you need some control on the 2-arm exponent of your interface and things like this. And so it's not straightforward to get.
Kind of connected to Tito's question, so is there an analog of the Loebner energy for the massive?
So it's a bit tricky because so the Loebner energy is something you get when you look at kappa goes to 0, okay? But to start with, you already have a family for any kappa, right? So, or let's say for kappa close to 0, like here I just have for kappa equals to 4, and in the massive setting, you don't expect to have a 1-parameter family. So you don't expect that. So you know you wouldn't have just you don't expect a 1-parameter family. You expect at least a 2-parameter family, because the way the mass changes can also depend. Like here it changes with the square. Well, the square of the modulus of the derivative of the conformal map, but it could change with some other power of the modulus. So typically, let's say, okay, maybe another way of explaining this is if you think about easing, what I've said, I gave 2 examples of near critical perturbation, and you don't expect the scaling limit of the curve to be the same in those 2 examples. So then you already have a kind of, you have already 2 choice for 1 value of kappa. So then the question of taking large deviation for massive SLE kappa, it's a bit tricky because for the moment you don't have you don't even have a way to construct a 1-parameter family or 2-parameter family or anything. So yeah, I don't know.
Right, if there are no further questions, let's thank Léonie and all the speakers.